Hello friends, welcome back to my channel. In this video, I am going to solve exercise question from book Topics in Algebra from chapter Vector Spaces and Modules. Question is, if V has a basis of n elements, give a detailed proof that V is isomorphic to Fn. Before proving the given result, firstly we will recall definition of a homomorphism in vector spaces. So, if U and V are vector spaces over field F, then the mapping T from vector space U to V is said to be a homomorphism if number 1 T of U1 plus U2 is equal to T of U1 plus T of U2, and number 2 T of alpha U1 is equal to alpha times T of U1 for all vectors U1 U2 in vector space U and for all scalars alpha in field F. Now note that we can express these two conditions equivalently as T of alpha U1 plus beta U2 is equal to alpha times T of U1 plus beta times T of U2. Now we are ready to prove the given result. So proof. Here V is a vector space over field F such that dimension of V is n. Now since dimension of V is n, any basis of vector space V will contain exactly n number of vectors. So let us consider B is a basis consisting of n number of vectors, say e1, e2 up to so on en. Now define a map, say phi, from vector space V to vector space Fn. Note that if F is any field, then Fn is a vector space over field F. Before defining this map phi, we need to recall the concept of coordinate of a vector in a vector space. So, let V over a field F is a vector space and dimension of V is n. If B equals to e1, e2 up to so on en is a basis of V, then every vector U in vector space V have a unique representation of the form U is equal to a1 e1 plus a2 e2 plus and so on plus an en, such that each ai is a scalar coming from field F. Now, because of this unique representation, the n scalars a1, a2 up to so on an are completely determined by the vector U and the basis B, and we call these n scalars the coordinates of vector U in a basis B, and we call this the n tuple a1, a2 up to so on an the coordinate vector of vector U relative to basis B, and we denote this by this symbol. That is, this is the symbol for the coordinate vector a1, a2 up to so on an of vector U with respect to basis B in vector space V. So here we are going to define this map phi from vector space U to vector space Fn such that phi of V is coordinate of vector V with respect to given basis B. That is, if V has a representation of this type a1 e1 plus a2 e2 plus and so on plus an en with respect to basis B in V, then phi of V will be the coordinate vector of V with respect to basis B, that is the vector a1 comma a2 up to so on an. Now we have defined this map phi from our side, so we need to show that this map phi is well defined. For this, consider two vectors, say v1 and v2 in vector space V, with v1 having representation of this type and v2 having representation of this type with respect to basis B. Now let this v1 and v2 are vectors in vector space V such that v1 is equal to v2. Now since v1 is equal to v2, their representations are also same. Now since these two representations are same, coordinate of v1 with respect to basis B will be equal to coordinate of v1, v2 with respect to basis B. Now this is coordinate of v1 with respect to basis B is the vector a1, a2 up to so on an, and coordinate of vector v2 with respect to basis b is the vector b1, b2 up to so on bn. Now since these two vectors are same, we have phi of v1 is equal to phi of v2. So we have considered v1 is equal to v2 and we end up with phi of v1 is equal to phi of v2. So our map phi is well defined. Next thing is to show that phi is a homomorphism. For this, consider any two scalars, say alpha beta in field F, and any two vectors, say v1 and v2 in vector space V, such that v1 have representation of this type and v2 have representation of this type with respect to basis B in V. Now consider alpha v1 plus beta v2. So alpha v1 plus beta v2 will be alpha times this representation of v1 plus beta times this representation of v2. Now simplifying this, we get this thing. So alpha v1 plus beta v2 has representation of this type with respect to basis B. So phi of alpha v1 plus beta v2 will be coordinate of alpha v1 plus beta v2 with respect to basis B, and from this representation of alpha v1 plus beta v2, we know that coordinate of alpha v1 plus beta v2 with respect to basis B will be this vector alpha a1 plus beta b1 comma alpha a2 plus beta b2 plus and so on plus alpha an plus beta bn. Now we can write this vector in this form, sum of these two vectors, that is alpha a1 plus alpha a2, alpha a1 alpha a2 up to so on alpha an plus beta b1 beta b2 up to so on beta bn. Now taking alpha common, we get this alpha times the vector a1 a2 up to so on an, and here taking beta common, we get beta times vector b1 b2 up to so on bn. Now this vector is the coordinate of vector v1 with respect to basis B, and this vector is coordinate of vector v2 with respect to basis B from representations of v1 v2 with respect to basis B. So we get phi of alpha v1 plus beta v2 is equal to alpha times coordinate of v1 with respect to basis B plus beta times coordinate of v2 with respect to basis B, that is phi of alpha v1 plus beta v2 is equal to alpha times phi of v1 plus beta times phi of v2, and therefore our map phi is a homomorphism. Now we need to show that phi is injective. For this we will use the theorem which states that a homomorphism phi from vector space U to vector space V is an isomorphism if and only if kernel of T is singleton 0. So all we need to show that the defined map phi from vector space U to Fn is an isomorphism, and we have shown that the map phi is homomorphism. So only need is to show that the map phi is 1 that is injective, and to show map phi is injective, we will show that kernel of phi is singleton 0. So let us consider any vector, say V, in kernel phi having the representation of this type with respect to basis B. Now as V is a vector in kernel phi, we have phi of V is equal to coordinate of 0 vector with respect to basis B. Now phi of V is coordinate of vector V with respect to basis B and RHS as it is. Now coordinate of vector V with respect to basis B from here will be the vector a1 a2 up to so on an, and coordinate of 0 vector with respect to basis B, all we know that is the 0 vector 0, 0 up to so on 0. Now since these two vectors are same, we have a1 is equal to 0, a2 is equal to 0 up to so on an is equal to 0, since their coordinates are same. So representation of V becomes, from here we can write V as Since all a1, a2 up to so on an are 0, so v will be equal to 0 dot e1 plus 0 dot e2 plus and so on plus 0 dot en. Therefore, v will be equal to 0 vector. Now, since we have considered v is any arbitrary vector in kernel phi and we get v is equal to 0 vector, so we can conclude that kernel phi is singleton 0. And so, by this theorem, we have map phi is injective, and so from 1, 2 and 3 we have the map phi from vector space V to vector space Fn is an isomorphism, and therefore V is isomorphic to Fn if V is a vector space of dimension n, and this proves our result.